This is our ME475 final project on the connecting rod. I'm Mitchell Hines.
And I'm Hai Nguyen.
The purpose of the connecting rod is to link the piston to the crankshaft. It transfers the energy from combustion into mechanical energy used to propel the vehicle. Our connecting rod is 234 millimeters in length, 73 millimeters in width at the base, and 38 millimeters in width at the arm, with a thickness of 35 millimeters. Connecting rods are commonly made from steel or aluminum alloys. The connecting rod undergoes two primary forces, tension and compression. The largest tension force coming from the intake stroke and the largest compressive force coming from the power stroke. Compression being the larger of these two forces causes a possible concern of buckling. It is good to note that the average operating temperature of an internal combustion engine is around 200 degrees Fahrenheit.
Looking at the data for a motor running at 5700 RPM, it confirmed that the force in compression is indeed higher than force in tension. In that graph, the maximum force is less than 15 kilonewton. So for our worst case scenario, we put compression and tension at 20 kilonewton. And for fatigue analysis, we use 15 kilonewton in 40 reverse cycle, which that's more of an average loading condition. In our analysis, we fixed the bottom ring and have the force only apply at the top ring in the actual direction only, because the graph showed there is no force in the normal direction, and we use structural steel as a material. We decided to use 3mm size tetrahedral element, and we refined the area of the fillet radius and the smaller ring because we believe that's where the highest stress concentration will occur.
The 20 kilonewton load and compression resulted in a von Mises stress of 75.5 megapascals and a total deformation of 0.03 millimeters. The area with the highest stress concentration is at the top of the structure where the piston would attach to the connecting rod. From the stress values, the factor of safety calculated based on the distortion energy criterion is 3.31, verifying the structure will not yield in compression. For compression buckling, the first 10 modes of buckling were computed. The first buckling mode had a factor of safety of 15.5. This factor of safety rules out the possibility of buckling before the structure yields.
Set up the tensile analysis the same way as in compression, with the exception of having the force pointing at the opposite direction, and the result will come out to be almost identical. The area of maximum stress is still at the top. With a minimum safety factor of 3.3, the connecting rod will not yield in tension. Fatigue analysis was conducted with 15 kilonewton load applied at the top in a fully reversed cycle. The Goodman mean stress theory was used to calculate the safety factor. With the safety factor greater than 1, we can assume infinite life for a connecting rod. We calculated the first 10 natural frequency of a connecting rod, with the first one at 29,500 RPM. This is much higher than any frequency an engine would be running at, thus making our connecting rod safe to use.
The results obtained from our tension and compression analyses are shown in the following tables, with a worst case scenario being 20 kilonewtons and an average engine loading case of 15 kilonewtons, which is a much more realistic load when considering tension. The 20 kilonewton loads are close to the same regardless of the actual direction, and as expected, the 15 kilonewton force shows a decreased stress and deformation. The possibility of buckling and fatigue can be easily dismissed, with their safety factors exceeding 15 and 1 respectively. The natural frequencies computed are also much higher than the normal operating speed of any engine.
To do a more complete analysis of the connecting rod, a transient structural study would be recommended, since the rod would be in constant motion. With our safety factor being above 1, that leaves us room for optimization in reducing the weight by reducing the width, the thickness, and the fillet radius.